Okay, we're going to do some volumes of rotation that are not around the origin. Okay, so numbers 1, 2, and 3, those are all pretty straightforward. Actually, we'll start with number 3. Number 3 sounds like an okay one to start with. Anyway, you don't know what number 3 is, so let me write it here. Number 3. Number 3 says we have two functions, the area between y equals x squared and y equals x cubed. And we're going to rotate this around the x-axis. Okay, so these have one point of intersection, actually 2 points of intersection. X squared equals x cubed when x equals 0 or when x equals 1. Right, those are the only times when 0 squared is going to equal 0 cubed or 1 squared is going to equal 1 cubed. So those are going to be your bounds of integration. So if you remember, which, well, maybe you do, right? The origin is where x squared starts, and then it goes to the point 1, 1. So here's the graph of y equals x squared. Right? And then we'll go to 2, 4, and so on and so forth up there forever. And then we have the graph of x cubed, right, which also has 1, 1 and 0, 0 as its point. 0 cubed is 0, 0 squared is 1. But it comes in flatter and then grows steeper. Okay, so x squared is actually the equation, or is it? I forget. Maybe it's less steep. Like that. I know, it's kind of hard sometimes remembering all the things that you have to remember. So this is the area that we are talking about. Okay, that area. And when we rotate that around the x-axis, we'll get a reflection of it down here. Right, we'll get a reflection where the bottom equation is x squared and the top equation is x cubed. Okay, so we're going to have this tiny little thing, but it always has a circle, right? There's circles when you rotate something around a central axis, we get circles. So let's look at a specific circle. How about this one here and that one there, right? Maybe when x is 1/2 or something. We're going to have the shape is going to be a washer, right? So we have the inside which comes from the graph of x squared, right? That's the distance in between here. And we have the outer circle from x cubed. Now we need to know what is the outer radius. Okay, that's the outer. So we'll decide how far is the outer radius from your outer radius. And then we'll talk about the inner radius. So every time we have one of these washer problems, right, there's a hole in the middle of your solid from revolving something. We have an outer radius and an inner radius. R1 and R2, we'll say. That's a 2. So the outer radius, how far is it from the center to the outer radius? Right, that would be this much to here. How far is that? That is the x cubed function. Okay, so the outer radius is whatever x cubed happens to be. That's the outer radius. That's the distance from 0 to that pink line. Now, what about the inner radius? How do we calculate that length right there? What equation does that touch? That touches your x squared equation. So if we want to find the volume of this solid when it's revolved around the x-axis, right? Volume is always pi r squared because we're taking the integral of all of these washers, right? We're adding up a whole bunch of areas. Volume is the accumulation of areas. So we start with this formula. Okay, in fact, we're going to start with a different formula. Well, it's the same thing. We're going to pull the pi on the outside. And for our problem, we just go from 0 to 1, right? That is our bounds of integration. They intersect at 0 and they intersect at positive 1. So from 0 to 1 is what we are looking at. Now the radius, right? The radius changes, and it's based upon, right, these guys. The radius of our function is always the outer part minus the inner part. Okay, the outer radius minus the inner is telling us the actual thing that's making our volume, right? That's the stuff in between. This is where your volume comes from, right? The sum of all of these areas of your washers. So the outer is x cubed and the inner is x squared. And that's the radius, right? That's how we find the radius of your function that we are finding the volume of. Okay, if you put that into the calculator, well, that should give you the answer, because we really don't want to do that by hand. It's possible, but we're not going to do it.
We made a mistake. Did you have to fix that?
So that's if we have two equations rotated around the x-axis, okay? So let's look at some alternative ones where we rotate it other than just the x-axis. So let's make up an equation real quick. Actually, it's from your worksheet. So we have the equations y equals x and y equals 0, right? That's the x-axis, and the line x equals 4. So let's graph this situation here. What do we have? We have a first quadrant, y equals x squared, which is the square root function, 1, 2, 3, 4. So at 1, the square root of 1 is 1, and at 4, the square root of 4 is 2. So we have this much of our square root graph. Okay, x equals 4 is our vertical line, which closes it off here. So this is the area that I am rotating. Looks like that. So let's put in our axis of rotation, which is y equals 3. So here's the line y equals 3. Horizontal line y equals 3. So when I rotate it, right, it's going to rotate this direction. Okay, it's going to rotate like that. So the bottom part here is going to end up where? It's going to end up here. When I rotate this shape around this line, it's going to end up here, right? The cross section will be up here. So we're going to draw this one's mirror up here, which is 1, 2, 3 units, right? So it's 3 units from the x-axis to our line of rotation. So this part is going to end up here, right? We have 1, 1, which is going to be there, and then here. So this is the reflected part, where the rotated part is going to end up there. So we're going to have this nice circular base, because anytime we rotate something, we get circular bases. Right? We're going to have a circular, this is going to be empty, right? That part will be empty because our graph isn't shaded in this part. So this is going to be the hollow part of our graph. And then we're going to have another, right, solid top. Basically, it's a cylinder with this, what's the part of the trumpet? What's that called? The bell? Is that called the bell of the trumpet? Those of you that are in band. The bell is the part out here that makes the noise go out in all directions. So it's a cylinder, right, almost like a toilet paper with not straight through, but this bell that has been subtracted in here. Okay? So we draw in our washer, right? We're always going to have a washer cross section when we have an open portion of our graph. Okay, so consider maybe this part when x equals 2, right? So we're looking at this cross section, which is going to be some type of a washer. So let's talk about the outer radius. How far is it from the center to the outer? So that's here, right? From the center to the outer. How far is that? That is always going to be 3 units. Okay, so the outer radius is going to be 3. So if this were a cylinder, it would have a radius of 3 and a height of 4. Right? Because this is 4 from 0 to 4, and the height of this thing is going to be 3. Okay? And what about the inner? So here's the inner radius. That goes from here to there. How do I figure out what that radius is? Well, that's my outer radius minus whatever my y value is. And how do I find the y value? By taking the square root of x. So my outer radius is always going to be 3, from the center of rotation to the outside part of your graph. In this case, that's 3 units because our graph is flat, right? This is the x-axis. The x-axis represents the outside part of our graph. Or we could go up to the top, right? If that's better, look to the top. How far is the top away? So outer radius is 3. Inner radius is 3 minus square root of x. Okay, so every time we have a problem with a hole down the middle or any type of openness in our 3-dimensional figure, we have to do this washer and find the 2 different radiuses. Because now the volume, hopefully, is not difficult to do. Okay? So we go from 0 to 4. That is our bounds of integration from 0 to 4 of our radius squared. Okay? How do we find the radius? It's always the outer radius minus the inner radius. The outer radius squared minus the inner radius squared. It's always pi r squared. So the outer radius is 3 squared minus 3 minus root x squared. So here we have 24 pi as the answer. Okay, well, let's look at part B. That's a little bit different. Here's part B. So it's the same graph, but now we have a different axis of rotation. Okay, so let's draw this again. Right, we have the point 1, 1 and the point 4, 2. That is our square root curve. And then we have x equals 4 and y equals 0, so we have this area that we're going to be rotating. But now that line of rotation is 2 units down. So here we have your line of rotation, 2 units down here. That means if we draw its mirror, right, our graph is going to end up down here. So 2 units, right, this is 2 units between the x-axis and our axis of rotation. So we're just going to end up 2 units below your axis of rotation. We still have the point here and there. Right, so this is going to be our shape. We'll have that circle in the middle, right? Circle at the end here. That'll be an open. So we're going to have basically an open cylinder missing from this graph, right? A straight cylinder. It's nice. It's straight edges. No curves down the center of this cylinder. That's going to be the resulting shape that we're going to find. Okay, so notice that we have a nice washer, right? Anytime we look at this, we're going to get a washer. we have, well, let's just draw the washer. Inner circle, outer circle. Right, so we have two radiuses. One is the outer radius. So how far is it from our center of rotation to the outer part of your graph? Right, that's your outer radius. So what is that length? Well, at one point it's 4, but that's only when x equals 4. What about when x equals 1? What is it there? What about when x equals 1.5? What is it there? Right, so we have all these different times, but in general, how do we find that? How much is it from the center to the x-axis? 2, and then how much is it from the x-axis to this point up there? It's root x, so we're going to add 2 plus root x. That's how we get the outer radius. From the center to any point along our shell, right out here, is going to be 2 plus the square root of x. Okay, the 2 comes from the fact that it's 2 units away from our center of rotation. And then how do we get this one? Our inner radius, what is this length in there? That's always going to be 2. Always 2. Okay, so now we go to our formula. We have our washer. We wrote down the two equations. Pi times the integral from 0 to 4 of the outer radius, which is 2 plus root x squared, minus the inner radius, which is 2 squared dx. Okay, so when you're putting this in your calculator, you're going to have to put everything in parentheses probably, so it does the calculation correct. Okay, so draw our washer every single time. We have the outer radius from the axis of rotation to the outside part of your graph. Right, in this case, that part is the actual function. Before, it was 3, right? Because it was a solid horizontal line. It was always going to be 3 units less something else. Okay, so put this one in your calculator. Draw your washer and find out what your 2 radiuses are from there. 88 pi over 3. Okay, so anytime we have a solid that has some of it missing, right? There's open space, open air in it somewhere. Draw your 2 circles, or your inner circle and your outer circle, so you can find their independent radiuses, or radii. Okay, so it's the distance from the center to the outside, wherever the outside happens to be, and then the distance from the center to the inside, right? Sometimes they're both going to be functions, like it was in that first example. The outer radius was to x cubed, and the inner radius was to x squared. So to find the gap, we subtract them, top minus bottom, and then we integrate. Okay, here we have holes, so we have 2 individual radii that we have to find the lengths of, and then plug into our formula, pi times outer radius squared minus inner radius squared. Okay, so good luck with drawing these. Sometimes they can be pretty tricky, but remember, we're trying to find radial lengths from the center of rotation to the outside and the inside.